Thank you very much. Thank you so much for inviting me. This is exciting to be here. So, quantum information. We have apparently 40 minutes to cover quantum physics and, basic algorithms and a little bit of mathematics, a little bit of matrix linear algebra, and then, at the end we'll put it all together. No, it's going to be a little bit of a potpourri here. I can't talk about everything, so we're going to focus mostly on particular algorithms and hope to give you a sense of how all that works. And the real question is what happens when a mathematician comes to a computer science program to discuss physics, which is exactly what's happening right now. We'll find out. I was at UC Berkeley last week, and I heard a talk by Jim Gates, a very prominent physicist, and even he was self-conscious about addressing a math department, right? Likewise, I'm very aware that I'm the mathematician in the world of the computer scientists talking about physics. So if you have questions, please hold on to them, because I'll certainly leave some time at the end to talk about it. So if you read the abstract, the idea is, right, that in our usual information theory, we encode everything in zeros and ones, and we don't care about the encoding, about the way that it actually physically happens. There's this model, and that's fine. In quantum information theory, though, the idea is instead, if we encode our information in the states of quantum systems, we see the weird behavior as a resource and not as an impediment, not as something we want to get past, but something we actually want to use. And this idea, which is what sold me on this field, more than 10 years ago. It's always fun to sort of use turning lemons into lemonade. Essentially, is what we're doing. So that's where we're going. In a little outline, we'll just do a little talking about classical information theory to make it clear where we're starting from. Talking about quantum. I'm going to talk a lot about superposition, which is the one of the fundamental properties of quantum, and give you a couple of examples of quantum algorithms. And then at the end, we can talk about other quantum properties that might be useful. Okay. So what is quantum information theory? It says, what would it look like if we try to accomplish information tasks by manipulating systems at the atomic scale, systems such as photons and electrons that are subject to the weird properties of quantum mechanics. And this is not such a theoretical question, right? As our components of our computing devices getting smaller and smaller and smaller, this is becoming relevant whether we like it or not. The question is, would such a computer or such a communication system be better, or more efficient, or more powerful? And the real answer is it would be different. And so it's important. You can choose for yourself. I'm not going to make bold claims that it's all these things, but it's certainly different. And in that difference, it can do things that traditional computers cannot. On the other hand, a quantum computer certainly can simulate a regular computer, so in some ways it's at least as good. So just trying to give you some teasers. Some of the early successes of quantum information, we were able to, Shor's algorithm, which is an efficient algorithm to factor large numbers, and almost at the same time, a algorithm to search an unstructured database, and then an algorithm for securely establishing a cryptographic key. These are sort of the big three early results, which sort of convinced people that this was a good idea, that it might actually work. And we'll talk about a couple of these. A couple things to notice. This is, on the scale of things, fairly recent, right? Nobody was really talking about these things very much before 1984. And sort of finally in the mid-90s, folks said, hey, this is actually interesting. So and then since then, that's sort of been what we've been holding on to, is hoping to do better. So today I have 3 goals. First of all, the one that you probably care the most about is to describe some of the things that a quantum computer can do, or a quantum information system could do, that are different from the sort of macroscopic computers that we're used to use. Again, 40 minutes. I'm just giving you a taste, right? That's all you're going to get. But I also want to use my perspective to sort of preach the idea that exploring new models helps you think about the traditional model, right? That it forces you to think about things that you assume that you completely understand. And I'm not going to talk a lot about that, but you'll notice it's in the background of a lot of things that I'm thinking about. And also just to point out the importance of varied perspectives. Right? I am a mathematician talking about physics to computer scientists. That's what I'm doing right now. And this material, mathematics is informing the physics. They're both informing the information management or computer science side of things. But then there's feedback, right? I get to study new mathematical questions that are motivated by the physics. We understand the physics better because we're asking these sorts of questions that are motivated by information tasks. So the interplay between all these different areas is very rich and mutually rewarding. So this is good. The idea that there are people, like, I'm going to say things today that a physicist could never say. Be warned, okay? Because that reflects my perspective. This is useful, okay? So that's where we're going, just to let you know. Oh yeah, sorry. What we want to talk about today is how to actually build a quantum computer. That's not what I do. So I happen to be a theorist, so that's what I'm going to talk about. And hope that's okay. Okay, so let's just remind ourselves for just a second of what of Shannon's model, right? 1948. This is Shannon's model of information transmission, but it is equally a good model for any kind of algorithm. There's an input and there's an output. So this is taken from, I think, Shannon and Weaver's paper. So this is the standard. This is on page 2 of every information theory textbook that there is. And this also would work for any algorithm where you have an input and you have an output. And the first step always is an encoding. Take your message and you encode it in some convenient form. And the thing I want you to notice is that both of these are labeled as the message. Both sort of the pre-encoded and the post-encoded. They're identified completely as being the same thing, right? And that's where we're going to make some changes. So I'm talking to you right now. I have an idea. I'm encoding that idea into sounds and to syllables. If I was to write these down, I would encode them into letters, into words. And of course, we could encode them into zeros and ones, right? And anything else. Not saying anything you don't know, but it's important that the form is not quite so crucial. This is a model, right? This is a model of information transmission, meaning it's sort of idealized. And this allows us to establish theoretical bounds on real-world systems which exactly match the model. But of course, such things don't actually exist, right? And so there's always this gap, always this noise between what your model says and what the actual system does and how it behaves. And traditionally, that has been your problem. If you're building a information management system or a database management system or whatever, and there's a gap between the model and the way your system is working, that's your problem. The theorists don't care, right? And so we're trying to share that a little bit. Okay. So as we said, everything gets encoded as zeros and ones. The most important thing is we need a medium which is stable and distinguishable. If we're going to try to input a bit, we need to be able to tell a 0 bit from a 1 bit. And if we come back 2 minutes later, we want a 1 bit to still be a 1 bit and a 0 bit to still be a 0 bit. Those are fairly important. And here's a couple of pictures, right? Traditional pictures. You can encode your bit as a open or closed circuit. I'm going to tend to be thinking about a bit as being just an on-off light switch. It's a good image. But it doesn't really matter. You have a true-false checkboxes, and that's the Old North Church in Boston. You can put 1 lantern or 2 lanterns in it and communicate that way. Okay, how it doesn't matter. The key thing is, if I turn a light switch on, it stays on, and that's there. Okay, so how is this different then? How is this different from what happens in quantum? Now, as we said, quantum mechanics is the model of very, 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 very small things. Okay? And it is strange. And this is my one slide history of quantum mechanics, which is in the 30s and before. But by the time the 1935 comes around, a lot of the basic ideas of quantum mechanics are established, worked out, the mathematics has been tested, and it really looks like it works. Like it matches experiment very, very well. And no one was happy. No one was happy because it's just, it felt weird. It felt strange. It felt wrong in some way. The mathematics was right, but didn't feel good. Okay? And so there's all kinds of hair tearing and whatnot. And now, it's 2015, and actually, to be fair, I would say the 1990s, we got to this place. Yes, quantum mechanics is strange. But it's not necessarily something to get upset about. And in fact, maybe we can try to do something good with it. And it really, with respect to everyone, right, it took at least a generation before people could let go of the idea that the strangeness is bad. And then some new folks can come in and say, no, not so bad. Okay, so now let's do this. So I don't care so much about the specific system that we use, but a specific quantum system that we use. But suppose you want to encode a string of zeros and ones. So everything that I'm talking about now is encoding classical information. So classical is what I say classical, I mean traditional, right? We didn't need the word classical information before I started talking because that's just what information is, but that's what I'm going to use. So classical information, which is zeros and ones, into a set of z spins of a sequence of electrons. So imagine, in a totally non-realistic way, that you have a whole bunch of electrons, and you just pick them up and you put them in a row, and you arrange. Electrons have a property called spin, with the spin in the z direction, and we set something to be, let's say, spin up if we want it to be a 0, and spin down if we want it to be a 1. And I'm going to pretend that that's easy, which it's not. Okay, it's not for any kind of long sequence. But we're having a theoretical conversation, so we can pretend things are easy. So again, spin up, but it's just a highly unstable light switch. The key thing is that if you treat an electron like a light switch, you're missing out. So the question is there a way that we can take advantage of the weird, not understood properties to make this work? And that's what quantum information does. Okay. Again, I've said the same thing a few times already, but if you've never thought about this before, it takes a little getting used to. So that's why I'm coming back around to it. Okay, so I'm going to spend a lot of time talking about superposition, and then I can talk a little bit about some other properties as well. So superposition is one of the weird properties of quantum mechanics, and I'll try to convey that to you. Okay, so let's look at the classical world. Okay, so this is 3-card Monte. There are 3 cards, and your job is to find the black ace, which doesn't look terribly difficult. Okay, but then if we turn the cards over and we shift them around and we move them, and I won't demonstrate for you, but you understand, right? You understand how this works. I was going to go with the silly baseball caps they have at the baseball games. Follow the ball into the baseball caps, but this is old school. So, okay, so we have these cards. There's 2 queens and an ace. We mix them around a whole bunch, and the question is, where is the ace? Okay, and we're going to assume that the game is being played honestly, unlike actual 3-card Monte, which means that at any moment all 3 cards are on the table. Okay, so we've done this. If you just close your eyes for a quick second, imagine that I'm mixing the cards around. Imagine that's not just a picture of a card, but it's actually a card. Who thinks that the ace is right here? Okay, this guy thinks the ace is right here. Okay, that's good. Who thinks it's in the middle? Cult people. Okay, very good. Okay, and of course everybody else must think that it's on the right. The thing that we should all agree, and I do have some real cards, but I'm not going to actually use them, but the thing that we should all agree is that it's in one of those 3 spots, right? If I'm actually playing an honest game, it's either here, or it's either here, or it's there. Not only that, but it already is somewhere, right? That the fact that we don't know where it is doesn't change the fact that it is. Does that make sense? So this gentleman bravely said that the ace was over here on the left. He's either right or wrong. We don't know which it is. We don't know which it is, but we do know that he's either right or wrong. Does that everyone on board with that? Again, things that are obvious until they're not. Okay. Okay. Now this is an introductory talk. Actually, I'm going to just focus on 2-card Monte, which is much less interesting, but it's the same. It's the same thing. So I want to keep everything base 2. Is really what it is. Same idea. So now there's 2 cards, and your job is to find the black ace. And that's what I just said, so that's fine. There's only 2 possibilities. Either the ace is followed by the queen, or the queen is followed by the ace. And one of those has to happen. Okay, and if we turn one of the cards over and see that it's the ace, then we know the other one is the queen. Oh yeah, okay, that makes sense. Okay, so what if we did this in the quantum world? Okay, where we encode the ace and the queen in the spins of our electrons. So if the first card is the ace, we make the first electron spin up, and if the first card is the queen, we make the electron spin down. And since I'm treating these as logical possibilities, I'm going to label spin up and ace as a 0 with a funny little Dirac notation, which just indicates that we're talking about a quantum 0 and not a regular 0. Okay? And once I do this, it's no longer important that it's the spin of an electron. It could be the phase of a photon. It could be any quantum system. Okay? So there, that we're going to encode the spin up the ace as 0 and the spin down queen as a 1. And as before, we can settle the question. Everything that we've done before works. We can measure the spin of the first electron, and if it's spin up, that's the ace, right? Then we know that the other one is spin down, which represents the queen, and vice versa. So in some ways, this looks exactly like what we did before, which is why it's reasonable to call them analogous situations. Okay, so what's the difference between using playing cards and quantum states? Well, what's new is that it's possible to prepare in this case, our electrons, so that before we make the measurement, it is not correct to say that the first card is an ace or the first card is a queen. Okay. So it's neither one. So that if you say that the first card is an ace, you're neither right nor wrong. Okay. So we say that our system is in superposition of the two possibilities, which we write as like this. I'm trying to keep the math to a minimum here, but I think we can handle this. So this again, this would be like ace and queen, and this would be queen and an ace, and this expression is what represents our system. They are in superposition of the two possibilities. I will mention, since the word is out there, that these two electrons are entangled with each other, and if I have time at the end, I'll come back and explain what that means. But okay. The important thing is the fact that we don't know which one, if it's 0, 1, or 1, 0, it's no longer a result of our limited knowledge, but an actual expression of the physical reality, or at least of how we set things up. If it's not just that we don't know, it's that no one knows, because it really isn't. The universe hasn't committed yet to which one it's going to be. And that is the huge difference, and that's what superposition is, right? It's the difference between, I'm trying to make the analogs with our familiar world as clear as possible, but we're leaving it behind here. And, hopefully you've seen some of this. And hopefully if you've seen this in the physics class, this is a different approach, a different take on it. Okay, and also, of course, if you've ever studied standard probability theory, which is a great thing that I enjoy teaching, it doesn't really apply here, right? The very first thing that standard probability theory assumes is that there is an answer. We just don't happen to know what it is. And that's just not what's going on here. Okay? Okay, so who cares? Why do we want this to, how can we use this? So this allows us to define something called a qubit as the quantum analog of a bit. And the word qubit was actually coined by my former colleague Ben Schumacher of Kenyon College, and it used to be the license plate on their minivan, on their family van. They drive around in the qubit van. It's very exciting. So he was one of the early pioneers in this field. So we know that a classical or a Boolean bit can either be in state 0 or 1. There's really only two possibilities. Whereas let's just look at that first card. The state of our two-dimensional quantum system is actually described by a vector. By a vector, and we usually think of vectors as looking like this. These are Greek letters, but they're harmless. And so it's some combination of an ace and a queen. These are just sort of coefficients that tell you how much of each you have. Okay, and I have it up there again. So the numbers alpha and beta, which are your coefficients, they encode two different types of information. How much weight is there on the first part relative to the second? So if alpha is big and beta is small, then you're much more likely to have an ace than a queen, a 0 than a 1, and vice versa. But there's actually more to it than that, because it also encodes what a relative phase is. Now, I'll show you a picture to help you understand what that means. But in all of these, and I apologize for the square roots of 2, but that's what the universe decided, all of these have equal weights on the two pieces, but their phases, these guys are exactly in phase. They both sort of have a positive sign. But now these are opposite phase because there's a negative between them. And then over there's an I, which is the square root of -1, which is an imaginary number. Yeah, we need that. So don't let that freak you out too much, but that's okay. So the best way to visualize the possible states of a qubit are as a sphere. So imagine you have a sphere, the north pole is 0, the south pole is 1, and you're actually allowed to be anywhere on the entire sphere. Think about this. Traditionally, a bit, you have a 0 and a 1, there's only 2 possibilities. Here, there's a whole surface of possibilities. Okay? Pick your favorite point. So this is incredibly rich. You have lots of freedom. That really is the word. You have lots of freedom to move around in this big space. You can just stretch out, and that's great. I'm going to use the globe as a little bit to help us visualize this a little bit better. Okay? So idea of a north and south pole are clear. For each point in the globe, the latitude tells you whether you're closer to the North Pole or the South Pole. Okay? If you're in the northern hemisphere, then you have more 0 than 1 and vice versa. But longitude then gives the relative phase. So all those points, states that I put on the board before, where the weights were equal, those are all points in the equator. And now you can sort of visualize, oh, wait a minute, there's not just 4 points on the equator, there's an entire continuum of points that are on the equator. And what am I talking about? I'm talking about, what's this a picture of? It's the picture of the set of possible states of your qubit system. That's huge. We can encode tremendous amounts of information in that. So that's really cool. So what happens then? So all of this structure is wonderful, and if we leave it alone, so if we somehow take our quantum system and we insulate it from the rest of the world in some perfect fashion, which again doesn't exist, but we can pretend, we can try, we can do a pretty good job. Left to its own devices, it's just going to evolve continuously and smoothly. So what's happening over time? This is sort of a time series here. Over time, what's happening? Well, the globe is spinning a little bit, right? The globe is spinning, well, in a counterintuitive way. It's spinning a little bit. Let's say it's a quarter turn to the right, and then as more time goes on, somehow it gets flipped over upside down. Okay? Anything you can do to an actual globe, you can do here. And the nice thing is that if the dynamics are understood, you can theoretically reverse this process, right? If I know that what's happened is a quarter turn followed by a flip, well, then all I have to do is flip and do a quarter turn the other direction, and I get back to where I started. And not just I get back to where I started, but every person, no matter where you start, right? If you start here in Central Africa, or you start here in Spain, or you start on the other side in South America, everybody gets back to where they started. Okay? So that's really nice. And that's what we call reversibility, which is actually important. But that's for a closed quantum system, right? It's perfectly insulated. What's the problem with only looking at closed quantum systems? Well, you can't actually learn anything from it. So here's I'm mixing my metaphors here, but that's okay. So the closed quantum system now is inside the box. It's happy. Everything's good. In order for us to learn anything, if we want to figure out what's inside the box, we have to open it, and then it's no longer a closed quantum system. Which means that whole reversible thing, that whole wonderful, that's not true anymore. Okay, so this is the paradox of quantum, and if that doesn't work for you, it's really, it's like Toy Story, right? Or like every child's fantasy, which is that when they're not looking, their toys are alive and just jumping around doing all kinds of crazy things. But then as soon as the child comes in the room, the toys are just toys again. Okay, that's really what's happening with the quantum. As soon as we walk into the room and start looking at it, all of a sudden it's going to act classical. Any piece that we look at will now collapse and act classically. Okay, so that's my image of the day. So this is the paradox, right? The paradox is that we have this rich structure which we can't learn anything from, or when we try to learn something from it, it destroys the structure. So, and just to quantify it a little bit, again, keeping the math at a minimum, it requires an n bit, so a sequence of n zeros and ones, requires just n decisions, n coin flips. Whereas an n qubit system, you actually need 2 to the n, exponentially many complex numbers to define it. So lots and lots of richness. But once we open the box, the amount of information that you learn is still just n bits, or still limited by n bits. And that sadly is true. Okay, so we can't extract more information from our system than we did before, but we can extract different information. Okay, and that leads me to Deutsch's problem. Okay, so this Deutsch's problem is something that was formulated by David Deutsch in 1985 to show that in principle a quantum computer could solve a problem faster than a classical one. And it's a very simple problem. So now I have a whole deck, and I choose 2 cards, and the question is, are the 2 cards the same suit? Okay. So classically, the only way to know, and I did want to have actual cards for this, right? So I picked 2 cards. Classically, the only way you can know whether 2 cards are the same suit is to look at one of them and then look at the other one. Okay? So you just learned 2 bits of information. You learned that this card is red, and you learned that this card is black. But we're actually only trying to answer a question which requires 1 bit of information. Yes, no, are they the same? We don't actually care which one's which. So, or almost 2 bits of information. So how would that be different in quantum? Well, so I'm going to use what I'm going to call a quantum oracle. It's like a machine that can read the suit of a single card. If I build a quantum oracle which can tell me that this card is red and this card is black, it also needs to be able to read these cards in superposition. So if I input the first 2 cards together, it should be able to read them off at the same time. So by using this, so we can use this quantum oracle just once, and it will tell us whether the suits are the same without knowing which suit either of them is. So it's a way, and I'm going to walk through it in a second, to extract 1 bit of classical information by consulting the oracle just once. Whereas when we have actual cards, you have to ask 2 questions. Okay. So let's try to explain this, and this is the basis for all quantum, or for many quantum algorithms. I shouldn't say all. So by using a little bit of ancillary qubit state, so a little bit of magic, we can effectively get the suit reader to flip the phase of each red card while leaving the black card alone. So if I have a black card, it remains as it is. If I have a red card, it changes sign. So let's think about this. If we initialize our input into a superposition of 2 cards, then I've gotten rid of the square roots. This is a superposition given by 0 plus 1. As we said before, this is somewhere on the equator, so I'm going to say Jakarta over there. And that's an equal superposition of 2 states. But notice that they are in phase with each other. They both have a positive sign. There are 4 possibilities, since the first card could be red or black. And so you can see, here are the 4 possibilities, and these are the 4 possible outcomes you can get. Okay. So you see what's happening. It's just changing the the sign of the red cards. And it's doing it all at once. You're inputting it the whole thing, it's doing it all at once. So notice that if the two pieces have the same suit, then they have the same sign, and they're in phase with each other, the top and the bottom. If they have opposite signs, then they're out of phase with each other. So the same sign means that you end up in Jakarta, whereas if they're out of phase, it flips you around to the antipodal point on the equator. Okay, so imagine the globe for a second. We started off in Jakarta, and if the phases are different, then they get mapped to the other side of the globe, which is somewhere in Colombia. Okay. And because they are opposite sides of the globe from each other, well, all we have to do is turn our globe over, and now they're at the poles, and those are the things we can tell apart. We can tell apart the North Pole from the South Pole. So anytime you have points that are opposite from each other, you can actually tell them apart. Okay. And the thing to point out is that in the process of answering Deutsch's question, we destroy any way of knowing whether these cards were red or black. We just know that they are the same. Okay. I wanted to do in a second expand on this by looking at the idea about searching an unstructured database, but let's just think for a second. So Deutsch's problem is important because it makes use of the quantum properties of the machine that can tell us what the suit of the card is. And again, historically, it was the first problem. It's sort of a toy problem, right? Historically, that was the first one that sort of said this might work. Now, searching an unstructured database, that's not a toy problem. That's a real problem. That's something we actually have to do. Okay? We often think of this as the reverse phone number problem. If you know what a phone book is. Okay? You have a phone number, you have a phone book, you're trying to figure out whose phone number it is. Good luck. Right? Hard problem. Okay? Not technically, but hard problem. Okay, so this is the searching the unstructured database. I'm going to use it because I like cards. That we have a deck of cards and we're looking for the ace of hearts. Okay, same idea though, right? It's somewhere. How do I find the ace of hearts in this deck? Well, I got to look at the first card, and I got to look at the second card. I got to look at the third card. Is there a better way to do it? Well, as human beings, I could throw them on the ground and we can be more efficient. But a machine looks at it one at a time. Okay? There's really nothing else we can do. And so on average, I have to get through about half the deck. So if there's 52 cards in the deck, it's going to take about 26 guesses. If there's 5,200 cards in the deck, it's going to take about 2,600 guesses. Not a simple problem, right? So what happens if we try the Deutsch's trick here? We do the exact same thing, but now if I want to encode a deck of n cards, it exists in an n-dimensional quantum system. Let's say n equals 64. So if I have a 64 card deck. I'm in a 64-dimensional quantum system, which is encoded just using log 64, so 6 bits. It's a 6-bit system, but nonetheless, it's existing in a 64-dimensional space, which is very hard to picture, right? The 2-dimensional space was inside the surface of a sphere, or was the surface of a sphere. The geometry is harder, but if you want to keep the globe in the back of your mind, that's not bad. We do the exact same thing. We create a superposition of all the possible states, and we ask the oracle, is this your card? And the oracle pretty much says no all the time except once. But it's happening simultaneously. So if there are 10 cards total and we're looking at, and it happens to be the second card, we start with the superposition of all of them, and all it does is it flips the sign of the one we care about. And now these are not antipodal points anymore. Okay, we want them to make 180-degree angle with each other. These are more like 120, something like that. So not quite so good. So this is, and if the size of your set is big, then this angle is very, very small. So compared, so because this change is so small, we can't just measure it right away and know which outcome it is. We have to repeat this process a bunch of times. And there's a great geometric sifting that happens, going back and forth between marking the state that we care about and then just reflecting around this particular vector. Now notice what's really cool here is I'm talking about reflecting, like it's just geometry, which actually is useful, right? We're even though this is all happening in an abstract 10-dimensional space, it's actually useful to talk about it like that. So we repeat it a whole bunch of times, and the question is, how many times do you have to repeat it? How many times do you have to go through this whole, we have to consult our oracle and go through this whole process? And the answer is that as long as we don't disturb the quantum system, as long as we keep everything in the box, then the number of times you're supposed to iterate it is about pi over 4 times the square root of n. The square root of the n is the important part. The pi over 4, I put in because I like it. And it's correct, but it's not as important. So the square root of n, this is an O of root n problem as a quantum problem. If we quadruple the size of our database, the algorithm only takes twice as long to run. Okay? Whereas for the standard problem, classically, if you quadruple the size of your database, it takes 4 times as long. And obviously that gets more and more dramatic as n gets larger and larger, the difference between the square root of n and n. Okay, so the bigger your database, the bigger your savings. The other thing that's great about this actually is it gives you the correct answer with extremely high probability. The bigger the n, actually the bigger your probability of being correct, which is kind of nice. So the larger your database is, the higher the probability is that that it's successful. So we just said that. It's important to ask though, is it significant, because a lot of people get hung up on this, is it significant that our algorithm contains an inherent small probability of error? And of course the answer is no, right? Because any algorithm, when it's actually run, has possibilities of error, and there are things you can do to mitigate it. The other thing to point out, of course, is that if on the off chance we get the wrong answer here, it's very easy to check, right? You just say, is this your card? And if the answer is no, then you just run it again. Okay, and then so now it's going to take you 2 root n. Still much better. Okay, so we're okay. That the probability of error here is not a significant quantum difference. The fact that the probability is inherent maybe is. So a couple things to just point out, so concluding on this. There are a number of strategies. The earliest successes from the 90s were along the lines that I just outlined for you. Okay? And in some ways, people have been frustrated that we haven't been able to get past this model. There have been actually several interesting approaches to writing quantum algorithms that didn't quite follow this. But this has been the most successful. You know, it's very exciting to be able to say that you can factor large numbers efficiently. So that's there. So it's kind of this weird balance, right? That the quantum algorithm requires just enough time to meander around the globe, Okay, just enough globe-trotting before then trying to extract the information. There's a very, very precise balance that you need to do. Okay, so you know, next week's class we'll talk about these. Right? So I chose to spend this time talking about superposition, but there's lots and lots of things you can do. Quantum cryptography, which is really the closest to actually being realized, which uses the uncertainty principle. If you're interested in quantum complexity classes or complexity classes in general, I don't know much about them, but I've seen the pictures. They're very interesting. Entanglement and non-locality, that's my particular area that I spend a lot of my time working in. Error correction. Okay, you have this rich structure of a qubit. That means more varied things can go wrong, right? And so the idea that you can do error correction at all is pretty amazing, and you can. And all these things. Lots of cool things. Quantum teleportation sounds very sexy, and it is, actually. It's very cool. And it makes up for the fact that you can't, you can't clone a quantum state, but you can teleport it. So you win some and you lose some. And if you have specific questions about any of these, I'm happy to chat with you once this is over. But there's just lots of good things. If you are interested in further reading, one of the amazing things is that this book, Nielsen and Chuang, what was published in the late 90s, still is like an amazingly good, relevant book in a field that's changed a lot. This is an undergraduate textbook on quantum cryptography, which is excellent. I can plug myself. This is my only paper I've ever written about algorithms, so I figured I should mention it. Similar to some of the things we talked about. And then, coincidentally, Aram Harrow, who's a physicist, just posted this essay, Why Now is the Right Time to Study Quantum Computing, just as I was writing this talk, and it has sort of the same purpose. So it's very accessible, so you might give that a read at some point. And then Quantum Magazine has done a couple of nice stories on quantum computing lately, so you might check them out as well. Okay, so this is a further reading, and we're almost out of time, but I'm certainly happy to take questions if there is time.